Okay, so good afternoon again. Uh, I hope you're having a good time. Yesterday, we started talking about galaxies, groups, and clusters, galaxies. And today, what I'm going to do is continue the discussion yesterday. We talked a lot about yesterday about what makes up these groups and clusters. We know that galaxies live in groups and clusters. Most of them live in groups, small groups. The smaller the more galaxies live in them and spend most of their lifetime in them. And as the cluster environment gets richer, um, you have more and more, you have fewer and fewer galaxies inhabiting such systems. But often they are more interesting because to an astronomer, clusters are very interesting and we study them. But um, we are increasingly getting to understand the importance of the group environment because that's where most galaxies are. It's like studying history, where you study the conflict between kings and queens. That's not history. What is history is how the life of the real people change over time. And most of the galaxies are in on the cosmic web, evolving most of their life on these little systems, and they slowly make their way, some of them, into the larger systems, which are on the crossroads of the cosmic web, and get into clusters. And clusters are interesting in that way, but none of the galaxies who are in the clusters show much of their evolution at that late stage. Most of the interesting things happen to them when they are isolated or in small groups. And so it's interesting to study them. And then today I'm also going to talk about the largest systems, which are superclusters, which actually have all these environments together, the groups, the clusters, the filaments. Absolutely. And so, and like yesterday, I'm going to just give you a very brief introduction to the subject. The subject is vast and evolving, fast evolving. And today we're going to talk about, yesterday I talked about the constituents of them. We talked about how stars, the baryonic components, stars, the gas, the dust, in between the galaxies in the clusters are important, and said that there is a big missing component. So you have these galaxy groups, which are small groups, which are important, but there are also these clusters which are rare, very interesting. But if you're studying galaxy evolution, maybe these are not the best places to study them. But the galaxy-galaxy interactions, as well as the importance of clusters, is to study the distribution of matter, dark matter in particular, in clusters. We talked about the dark matter component being overwhelmingly large in clusters. And we also talked about how the baryonic component, there's a lot missing because we still, in our observational studies, don't probe the really faint parts in between the galaxies. And thus, we don't see the stars that are in between, or even some of the gas, etc. We talked about how galaxies are in small groups mostly. Here we're talking about the baryon budget, and there's a huge difference between the number of baryons that we find and the number of baryons that are predicted by the cosmic microwave background. Now, today we're going to talk about how to detect the more important, more prevalent matter, and that's the dark matter in galaxy clusters. and And there are three ways of doing it. Yesterday, we talked about the galaxy velocity dispersion, the random motion of the galaxies, the Fritz-Zwicky's method of using the virial theorem to find the dynamical mass of clusters. And this was pioneered in the 1930s, as early as that, even before people knew about dark matter. And he found that there's a lot of matter that's missing. And so he called it missing matter. It is the problem with it is it's model dependent. It depends on the virial theorem. The application of the virial theorem requires the system to be spherical and equilibrium, and also not expanding or contracting right now, which means that they're not interacting. You see a lot of galaxy clusters and groups are doing that, and so hard to use that assumption. Another way, and today I'll talk about two other ways. One is galaxy clusters have hot gas that are bound by that dark matter. and then talk about a little bit about gravitational lensing. You will have lectures on gravitational lensing in much more detail in the course elsewhere. And here I showed you this picture of the diffuse emission of gas, the hot gas, the 10 to the power 7 degrees gas in between the galaxies in rich clusters. And you see them in groups as well. It's not just rich clusters that have them, except that they have more than groups have. And you can see, if you just take away the galaxies, it's diffuse, and it can go as far as 1.5, 2 megaparsecs from the center and fill the whole cluster. We don't know what the whole cluster means, but at least the central region where the galaxies are. Now, here's an example taken from some work I did very early on that got into the ROSAT calendar as the calendar image of that year. It's very interesting. You can, if you compare the early images of clusters taken by X-rays, which is on the right-hand side, and the optical image of clusters, same cluster on the left-hand side. Now, if you look at both, you'll see they're actually the same cluster, except that what has been done is that the galaxies themselves have been exaggerated a little as ellipses. So that galaxy, for example, is that ellipse. That galaxy, this spiral galaxy, is that there. This galaxy is that ellipse. The stars have been taken out, and you can see a lot of these galaxies. Same thing, except that on the left, when you see just the stars, just the optical image, you don't know that there's a cluster there. Whereas on the right-hand side, when you look at the X-ray gas superposed on it, and remember, all these things on the left are stars, which are about 10 to the power 3 degrees hot, a few thousand degrees hot. On the right, you're seeing the gas that is 10 to the power 7 degrees hot. That tells you where the mass is. It tells you that there are two clusters in there that are merging together. But both of them are pretty spherical, but they're very close together, right? And what's holding them together is the dark matter, which you don't see in either of these two plots. You see optical light, you see X-ray light, but from that you infer the fact that in order for this gas to be so hot and in dynamical equilibrium, there has to be a huge amount of matter whose gravity holds them together, such that the potential energy and kinetic energy add up for the use of the field theory. Right? So from the X-rays, so what Zwicky did was look at the galaxies, and then by looking at their random motions, found the mass, a way of measuring the mass. In this case, what we'll do is we will put X-rays of the cluster and infer how much matter there is. Again, there will be some assumptions. There will be some assumptions of equilibrium. There will be some assumptions, and this equilibrium will be hydrostatic equilibrium, which I'm going to come to in a minute. Now, sorry. Yeah. So what you do is you essentially take these clusters and assume them to be spherical for simplicity. Now, there's quite a lot of work that has been done on non-spherical clusters as well, but I can't cover that in an introductory lecture in that. People work on this. So if you have spherical, then you divide this into shells, and then what you're seeing is a two-dimensional projection of the matter in these shells, right? And for those of you who are not afraid of actually using a little bit of mathematics, you can use these projection and deprojection formulae that can be worked out for shells, right? And this is quite a general problem that is used for a lot of spherical geometry in various parts of physics, not just in astrophysics. So what we do is we assume hydrostatic equilibrium. When you've looked at stars themselves, how stars have equilibrium, our sun has an equilibrium which has a pressure gradient, and that pressure gradient balances the gravitational collapse of a gravitating object. It's exactly the same thing. You think of the whole cluster as a ball of gas, right? And the galaxies are in. But the ball of gas, the hot gas, as I said, has already more mass than the stars and the galaxies themselves. And then that ball of gas, and with the galaxies floating in them, is sitting in a whole bath, as it were, of dark matter, right? So there's a pressure gradient because of this, the fact that there's maximum pressure due to this gas trying to contract, and the mass itself also putting pressure on the test particles that we can see, which is the hot gas. The pressure is maximum in the middle. It is zero on the outskirts, and so there's a pressure gradient, and that's balanced in normal hydrostatic equilibrium equation, which you must have encountered in many, many different parts of astrophysics. We use the same kind of approach, and that gives you Gm over r squared times rho. That's your dPdr. And if you go out in shells, as I showed you, then if you take a shell in a sphere, if you take a shell at radius r, then the mass interior to r, up to r, is the thing that goes in there, right? And then the rho in there is the average density within that r. Okay. For the time being, you can put that rho as constant as well, but in a real cluster, it's not going to be constant. So it's worth keeping that rho as a function of r. So for each shell, you can then apply the perfect gas law, an ideal gas law, assume that the gas that you're dealing with in this hot gas is an ideal gas. That's actually a very, very good assumption, because what happens is that at 10 to the power 7 degrees, the gas is actually a plasma. And in plasma, as you know, the electrons come out of the atoms and are freely moving around. And so the interparticle distances are very large. And so it actually, even though the densities of these things may be very high, but for all intents and purposes, this is an ideal gas. That's what an ideal gas here in the lab is also the fact that the size of the particles themselves is much smaller compared to the interparticle sizes, and that's one of the reasons ideal gas laws work. So these two together lead to this set of equations, and I'm not going to go and derive everything, but I'm just saying that these are the assumptions that go in. If you want to follow up, you can read them up. These are all in lots and lots of textbooks and on the web. What you do is you take these two together, put them together, put T as a function of R. You're looking at different shells. Each shell has a different temperature and pressure and density, and they're all in hydrostatic equilibrium. If you do that and you have spherical symmetry and equilibrium condition, you get something like this, an equation like this. What are the terms in this equation? Let's look at this in detail. So the terms in this equation are the rho, which is the density of gas, which actually can be measured. The temperature, which is a parameter. It's a function of R. Rho is also a function of R. This mu mh is actually the chemical composition of the gas. It's a way of representing the mean mean particle mass. So mh is the mass of the proton, and mu mh is a factor that tells you what is the mean particle mass in this gas. And it turns out it's mostly hydrogen, but it is hydrogen plus a little bit of helium plus a little bit of other things, and so that mu will turn out to be something like 1.3, 1.4, something like that. In this particular case, because it's ionized, it turns out it is half that, because each of these are create two particles, a nucleus and an electron. So it is weighted by the electrons have no mass, but it increases the number of particles. So mu is a factor that comes out of the physics. And then in this bracket, you have the density gradient and the temperature gradient. Okay, and if you can measure these things, then you can measure mass. So you want to measure the total mass of a cluster, including the dark matter, out to a certain radius, you can see the things that you need to measure is the density gradient and the temperature gradient of the, and so for each shell, what we do is we fit a certain model of what is causing the emission, and it has the temperature and the density as three parameters, and that gives you a measurement of the temperature as a function of radius, etc. And then once you can do that from an X-ray observation of a cluster, the pictures that I showed you, you can get the mass straight. So you can see that here's an X-ray observation of the Coma Cluster. The Coma Cluster is the same cluster that Zwicky measured the mass of by looking at the random motions of the galaxies. And in this specific case, what you're doing is you're looking at the X-ray gas, which is on the right-hand side of the same cluster, and you can see. So what you do is you break this up into shells and project the shells onto two dimensions, and then fit models of the emission, which I'm going to talk about in a minute, what the emission is, in each of these shells, and then you get temperature of this gas as a function of R, and you can measure the density also as a function of R by looking at the amount of X-rays coming from each of these shells. Remember that you're dealing with a spherical system, but you're actually seeing them on the sky in two-dimensional. That is why the projection effects are so important, but that can be handled mathematically. Once you can do that, then these things, so the temperature gradient and the pressure and the density gradient, both, if they're measured, can in principle give you M if you know the mean temperature. This is the Boltzmann constant, and this is the mean mass of the particle, etc. G, those are constants, right? What is this causing this emission? So you need a model to then break this up into shells and say at each point, the temperature and density is this. And that is what is known as thermal Bremsstrahlung. And I hope you've come across this before. Thermal Bremsstrahlung is nothing but if you have a thermal gas, which is called in thermal equilibrium, it of course emits as a black body. But what also happens is that the particles are accelerating in this system, and these accelerating particles themselves, because of their acceleration or deceleration, let out radiation. So these lectures have been covered, and so you get something like this. And the most interesting thing to note is that the emissivity of a gas that is in thermal equilibrium is proportional to the square of the density of these particles. There are two ends in there, the ion density and the electron density, which are the same because you take one atom, break it into an ion and an electron. And it is proportional to t to the power minus half. Okay, so it is related to the temperature and it's related to the density. So if you take these emissions in each shell, take the emission, you take a model, which is a physical model, which I'm not explaining very well here, because that will require lectures to go into, but they have parameters that have the density and the temperature as parameters. And you see the amount of X-rays that you're getting. In the X-ray observation, you not only get the brightness of the X-rays that you're getting, but you also get some information about the energy, because X-ray detectors detect both the energy and the flux. So you can fit that information in each of these shells and get as a free parameter the density and the temperature at each distance, right? Once you have that, then from the density gradient and the temperature gradient, you can find the mass. So this is a completely different approach from the dynamic approach that I talked about, which comes from the virial theorem. But it still depends on the assumption that it's in equilibrium. Because if it's not in hydrostatic equilibrium, this won't work, because remember, we use the hydrostatic equilibrium. and the properties of the ideal gas to come to this. Let me see, there are questions in there. Okay, so Shubrata Sarangi has a good question, and that's how do you handle the discontinuities in densities in the shells of spherical clusters? There's no discontinuity really. It's arbitrary where you put the shells. You can do it many different ways. You can divide up a spherical. It's continuous medium, right? It's a continuous medium, so you can. There are no. I mean, here you see red and yellow and green, and that's just a color code that is being given because of the color scheme that was used to plot this, and that color scheme is just just a function of the amount of light, X-ray light coming at that point. It has nothing to do with the temperature or actual color. It's a color scheme just an artificial color to show the change in flux or luminosity of the X-ray emitting plasma. And so there is no discontinuity there. It's just a discontinuity in the color scheme. In the actual observation, you can smooth it out to the level of, if you think that the photons are discrete, because in X-rays, the photon energy is very high, so you get a finite number of photons. This particular observation on the right probably has 20,000 photons or something like that. And to do that, to produce this plot, one has had to put them all together and smooth it with some Gaussian or something like that to make it look continuous. So where you put the shells are very arbitrary, and typically what people do is do it with do the same exercise with different placements of the shells, and it's all you need to do is to get a gradient, right? So actually you can get that with 3 shells. You can get that with 10 shells. It depends on how much data. I'll move on and I'll come to the questions later on. There are more questions coming on chat. I'll pause and ask you to do this later on. Right. Thanks. So this is one way of X-ray emission, and there are other complications that I'm not going into here because I can give you a whole course on X-ray emission. But the interesting thing is, it's not just thermal emission that causes the X-rays. It's far more complicated than that. That's what keeps us in business. The more complicated it is, the more astronomers we need to work this out. So there is line emission. The plasma, I said, is mostly hydrogen, but there are all kinds of elements in there, in the gas in between the galaxies. In clusters, there's silicon, there's magnesium, there's neon. As you can see, there are ion lines all the way up to iron in the periodic table. All those elements are there. They themselves have various emission lines and absorption lines in the spectrum, as you can see. This is actually a part of a spectrum of the X-ray spectrum of a gas in a cluster, and you can see everything is there, right? They're much in small quantities, but they're very important in the emission and absorption and cooling and heating and stuff like that. And it's very, very interesting to study the physics of this kind of plasma. But all that is taken into account in these models that we use. There are people who are working on the thermal Bremsstrahlung models and putting in line emission and stuff like that, write millions of lines of code to actually make sure that this ion K line is an ion atom which has 1 or 2 electrons left, and everything else has been ionized, right? So to figure out what the lines are, what the energy levels are that produces these lines, one needs to do very, very interesting atomic physics using very, very interesting quantum mechanics. And people do this. And people have been doing this for decades. And finally, we have plasma models of these highly ionized species of atoms that you get in the intergalactic gas in clusters. And that's one of the reasons it has taken such a long time for us to apply these things. And these models started becoming very sophisticated in the 1990s, 1980s, 1990s, and is still getting more and more improved and it involves a large number of nuclear and atomic physicists to work out these things. Okay, so I'll move on to other things there. So that's another way of finding that, and even then, as you saw when I showed you the Coma cluster, the mass of the Coma cluster from X-rays is about 5 times and 15 times the mass of the Sun, which is not very far from the 3 or 4 times 15 mass of the Sun that we got from the Zwicky method of the using the Whewell theorem. So actually, they're consistent in this case. There are other cases where they wouldn't be consistent because a cluster really has to be in very nice spherical equilibrium, and many clusters are very messed up. And so the dynamical result and the X-ray result will give you different answers. But let's move on to a system in which you will not have this this dilemma, because you can actually measure the mass much more directly without assumptions of equilibrium, and that is the case of gravitational lensing. So is Debarati still there? Debarati, can I ask you a question? Okay, so the people who are here, you have not done the gravitational lensing lectures yet, right? Can any of the students answer? Has the gravitational lensing lectures happened? I don't have the things in front of me. Can somebody put it in the chat box? Not yet. Okay, good. No, that's gravitational waves. But gravitational lensing will be Surud and Anuprita. That's from tomorrow. Good. So I just wanted to, because this will be a little introduction to gravitational lensing then, because I have to tell you what it is in order to see how it's important in clusters. So Einstein's idea, as you know, was that gravity, and Shunjit has already said this in the context of gravitational waves, is that gravity is actually mass bending space. So space, it's not a force. It is the fact that where there's mass, then space-time is bent. And interestingly, in Newtonian physics, light has no mass, so light cannot be bent by gravity. Whereas in this kind of approach, in which the fabric of space-time itself is bent by mass, right? Light can bend because it follows the shortest path between 2 points in space. So it goes along space-time, and space-time itself is bent, light can bend. Now, if light can bend, and so this is a big difference between Newtonian physics and Einstein's physics, and the fact that light can bend. And if light can bend, then you can have optical illusions. So if you have a star that is here and light bends by passing another star or a galaxy and coming to you, then you see it there, right? Just like refraction of a stick in water. So then this bending of light can be then used to have lensing effects, and that's the whole point here. So tomorrow, when you get the lectures on gravitational lensing, you will see that in great detail how this happens. But I'm going to talk about this in the context of clusters. So you have a galaxy that's very far away. You are here on Earth with a telescope, and you're looking at this galaxy. And as the light comes through a cluster, which is full of dark matter, as I said, in a cluster of galaxies, lots of galaxies moving around, and it's a whole bath of dark matter, then the light that comes through bends and comes to you. Okay, this light path also bends and comes to you, and so you see this galaxy here, you see this galaxy here, same galaxy in 2 different places, and you can see it actually in many different places, the same galaxy, because the light bends as it comes to you. Okay, now this is called gravitational lensing. Now this bending, and if you take that as an angle alpha, for single stars, the light bending causes a deviation of microarcseconds, which is very tiny. I said earlier on that it's very hard to measure things from the Earth that are much less than arcseconds. Microarcseconds are very difficult to measure. But for galaxies, this bending can be of the order of arcseconds. For clusters of galaxies, it can be much bigger. Okay. And what happens is when a lens, which is say a galaxy or a cluster of galaxies, is right in front of you with the actual object that is the source of light exactly aligned, then in this particular configuration, you will see that there is no preferred direction. So it can come from that direction, it can come from that direction, it can come from this direction. So you should see a ring. And this is called Einstein Ring. And this was proposed in the 1960s by Sir Revsdahl and various other people, saying that you should actually see many cases where a distant galaxy appears as a ring. And if they're slightly displaced, the lens and the source, then you should see that the ring would break up and into many, many images. And so that's the idea. You have a distant galaxy, a lens galaxy, and here on Earth, and you essentially either see a ring if they're perfectly aligned, or if they're not perfectly aligned, they're slightly different, slight deviation, then this ring breaks up on the circle into different parts of the image, right? So, and we started observing them after Hubble Space Telescope went up. So, and then many other telescopes, even telescopes on the ground, now see these Einstein rings. This is a good example of a Hubble Space Telescope image of a ring that was first seen. So here, a galaxy, and the blue galaxy that you're seeing is actually a very far away galaxy. It's one galaxy, but you're seeing it in the form of a ring, right? There are many such examples. These are this is a radio observation of a galaxy that's in the form of a ring. Now, the interesting thing is, once you see this as a ring, which is just a small galaxy in the background being distorted in the form of a ring, you know exactly how much matter is needed to make the light fold to make that ring. And so you can figure out what the mass of this galaxy, the lens galaxy, is straight away. You don't need any equilibrium conditions, etc., etc. This is a geometrical effect. Fermat's principle. You're following light, and you can do light ray tracing, and you can figure out how much the light bends and how much mass is needed to bend that light by a formula like this. And this gives you the size of the Einstein ring given amount of mass that you have, and then you have the mass, including the dark matter. That's the idea. Okay, so the first such multiple image, not a ring, was found in the 1970s as two identical quasars, and it was realized they're actually the same thing, just multiple images. And then came the quadruple one in 1985, and many of these are now found everywhere. Okay, so here are famous examples of slightly misaligned rings which are broken up into quadruple images, right? So 4 images, and all 4 images are of the same object. So that this is a very bright source in the background being multiply imaged by a foreground galaxy, and then you get the mass of the galaxy. For a cluster, it becomes even more spectacular. And that is because you can have much more complicated effects than just multiple images. You can get distortions, which are to do with the geometry of the. So here's a good example. One of the best images ever taken by the Hubble Space Telescope, Able 2218, and you can see all these distorted galaxies. There are hundreds of them in there, and these are all little galaxies in the background, but the dark matter of the foreground cluster is making them distorted, not just distorted, but multiple copies of them, right? So that galaxy and that galaxy are the same galaxy, but you're seeing them in 2 different places. Okay, and what happens is, here's a simulation of this effect shown by Sarah Bridle, who used to be a wonderful gravitational lensing a pioneer of modeling these things. Nowadays, she's become a professor of environmental science and left behind gravitational lensing. But she did these amazing simulations of of her face being lensed by a blob of dark matter and what it would look like. And you can see that here is her face, and then as you bring a blob of dark matter in front of it, you will get the face distorted in many different ways, and also multiple copies of them, right? So if you have, for example, a nice checkerboard of colors, and you brought some dark matter in front of it, it can make a very distorted image of us. And if you had this distorted image and you knew something like this was there, you could tell how much matter is needed to form this very nice Picasso image out of it, right? And this is exactly what you're seeing here, right? You're seeing lots and lots of galaxies being distorted and multiple copies of them being formed everywhere. This is the direct way of measuring masses in clusters. And now, with large telescopes and telescopes in space, we are now seeing amazing examples of these distorted images. This is just from one cluster, the cluster that I've showed you in many other pictures as well, 1689, which has a lot of these images, and these are details. If you just take it, if you just Google this image, the Hubble Space Telescope image of Abel 1689, then just expand different parts, you will discover yourself lots and lots of things. And there are whole PhD theses that have been done on little systems like this, where you try to model what could have caused how much deviation is needed to have a shape like that from a galaxy that's far away. You can take a spectrum and actually measure the distance of the galaxy, and then find out, the distance of the cluster, and from that geometry find out how much matter is needed. And so we have a very good map of the dark matter of Abel 1689 from lensing. In the lectures in gravitational lensing tomorrow, you will see that there is another version of lensing called weak lensing, which is if you can't measure the distortion of many of these galaxies, which are so tiny, you can't measure the distortion of each of these galaxies, but you can do it in a statistical sense, and you can club them together and have a statistically significant pattern emerging of the distortion of galaxies due to the presence of dark matter, and that's called weak lensing, which Surud and Anuprita More are going to talk about, and that also leads to more modeling of the matter, and that can happen in all kinds of systems, not just clusters. I'm just going to mention it here and not talk about it. And then, of course, there's cosmic shear, which they're going to talk about. What I want to impress upon you here is this. These are 6 clusters of galaxies, rich clusters of galaxies. Okay, and in this, we put together 3 different maps all together. The white and black are the actual optical image of the galaxy clusters, right? So you can see the galaxies in starlight. Okay. The X-ray emitting intergalactic medium is here in pink or red. Okay, and this is from, say, Chandra or XMM, one of these X-ray observatories in space, providing the X-ray emitting gas. And from this itself, you can map the dark matter and find the mass of the cluster, as I showed you from the thermal Bremsstrahlung. The blue part is the dark matter from the lensing measurements. So from weak lensing and strong lensing together, by modeling the distortions of the galaxies that you see that don't belong to this cluster but are in the background. And you can distinguish between the two by measuring redshifts of everything in there. And that will tell you which galaxies are in the clusters and which galaxies are in the background. And the ones that are in the background, you look at their distortions and figure out how much the light has to bend when they're passing through this cluster, right? Now, the interesting thing is you can look in these plots and see the comparison between where the dark matter is and where the galaxies are. In this particular case, it's very similar. The dark matter distribution seems to be all around the galaxies, right? Here, in this case, it seems to be all around. But here, it looks like there's a blob of dark matter here, a blob of dark matter there. And now, you also have the X-rays, right? So if you put all 3 together, you get this. And this is now causing a lot of very interesting observations in this whole field. First of all, you can see the clusters come in all kinds of situations. There are nice clusters which seem to be quite symmetric. The blue, which is the mass distribution, the dark matter distribution inferred from lensing, is nice and round. And the pink, which is the X-ray emitting gas, which is right in the middle, like I showed you for the Coma Cluster, and the galaxies are nicely distributed all around. But look at this case in which the mass seems to be here, the X-ray gas seems to be there, and galaxies seem to be all over the place. So clearly, this is not a situation in which you can apply the virial theorem. This is what has happened, is that you have two galaxy clusters that have collided and have gone through, and the gas is gone, and the mass is somewhere else, right? So the more we learn about these systems, the more details seem to emerge, which are very, very interesting. And then the naive approach that people had decades ago, where they modeled clusters as nice round systems, is going. And the best example of this is so-called bullet cluster. The bullet cluster was discovered about 10 years ago, and the idea is that the is the same color scheme where the X-ray emission is in pink. The blue is where the dark matter is, as inferred from lensing, gravitational lensing, and you can see that they're displaced from each other. And the galaxies are there all around. So the inference here is a bullet cluster is called a bullet because it's a high-speed collision of two clusters of galaxies, in which what has happened is in the middle, the gas, which is the baryonic component, is stuck in the middle. And as one cluster has gone through the other, the mass itself, which is the dark matter, which the dark matter is not collisional, it does not stick. It has gone through and is carrying on and is moving on. And it's not a system in equilibrium at all. It is just the result of a collision between two clusters. And people have modeled this in great detail by looking at the dynamics of the galaxies, the temperature of the gas, and the dark matter, etc. So these are very interesting cases, and many of these are now being found. Here's another of these, which seems to be similar, in which the dark matter seems to be displaced from the gas itself. So I'm going to pause here and look at the questions. There's a question in the chat box. Vinisha has asked, you said that dark matter is not a universally accepted theory. I did not say that. Dark matter is completely an universally accepted theory. Now, initially when it came to be in the 1960s, which is 60 years ago, when they were first discovered by Vera Rubin and others, then people started building alternative models that will explain away the dark matter, but nobody's found any yet. I gave an example of MOND, which is the modified Newtonian dynamics, which had some very famous backers, but it could not explain the presence of dark matter on all scales. In particular, after gravitational lensing started being used to model the mass, the modified Newtonian dynamics does not fit gravitational lensing at all. Okay, so that's a question. I'm just because I'm pausing here for a couple of minutes. I'll see if there are any other questions. Can people put up their hands or ask questions if there are any other questions so far? I talked about X-ray observations measuring mass. I talked about gravitational lensing measuring mass, and you'll get a little bit more of the gravitational lensing in the gravitational lensing lectures. Are there any other questions? I don't see any others in the chat box. Yes, go ahead. Your hand is up. Please go ahead.
Hello, sir. Am I audible?
Yes.
Sir, in this second picture in the top row, this Mac J0152. Sir, in that you told that on one side there is this X-ray spectrum, and on the other side it's this
Dark matter, yes.
Like dark matter, yeah, the entire thing has been shifted, and this is because of some collision of two clusters. So, sir, can we say that the dark matter in both the clusters also interacted with each other, because of which it got shifted on one side?
No, actually, under this pink stuff, there is also dark matter. If I take away the X-rays, you will see blue in there. So it turns out that in this is a, a collision in which all the gas, X-ray emitting gas, has ended up on one side, and the other side does not have as much, right?
So it's not evenly distributed, right?
Is not evenly distributed. That's the idea. And but the dark matter itself, because we know that these are particles, and we've never detected this dark matter yet. So we know that dark matter is just it's not they don't actually form compact objects like stars. They don't stick to each other. They are non-interactive, and so as two dark matter systems interact, they interact only through gravity, but when they collide or go through each other, they don't stick. The stars would stick. The matter, the baryonic matter would stick because they have attraction between each other, which are non-gravitational. But dark matter is just particles, so they just go through each other. And this is what's happening and this happens in simulations as well. There are a lot of people who've simulated dark matter in the form of massive particles. These clusters have been simulated, and you can see that these things don't stick. If dark matter actually interacted to stick to each other, then they would form dark stars. They would form dark objects. Those things are not found. They are not seen anywhere. Right. So dark matter only exists in diffuse form in the form of particles. Okay.
Thank you,
So
sir.
let's see whether there's any other questions there. Only yes, that's right. Absolutely. Hariharan asks it. Dark matter seems to show itself only through the measurement of masses. In gravitation, there are gravitational effects, and measurement of mass is a gravitational effect. There is another thing which is, for example, bending light, which is also an effect of gravitation, right? It's not necessarily measuring masses, but yes. Is it possible to detect dark matter for systems of smaller masses, like in the solar system? There is dark matter exists only on very large scales. The effect is much more on the effect of, for example, on the Earth or in the solar system. The amount of normal matter compared to the amount of dark matter is much more. So the effect of the dark matter is very small. Dark matter, you can see, is very evenly distributed, but the net density in dark matter is smaller compared to the normal matter on scales of the solar system or stars. But if you look at scales of a whole galaxy, then the outskirts of the galaxy, where the stars go down, the dark matter dominates. And on the scale of clusters, there's much more dark matter than there is star matter. But on the scale of us, for example, the amount of dark matter that is around me is very tiny because I'm very dense. Similarly, the solar system is very dense compared to the density of dark matter. So the gravitational effect of the dark matter doesn't play a role. So I will move on, and in the next 10 minutes or so, I will cover just an introduction to the largest structures in the universe, and that's called superclusters. So in cosmology, in Dr. Pranjape's lectures, you saw that when you actually do cosmology, you look at the basic thing. It's called Cosmological Principle, which is that the universe on the largest scales is homogeneous and isotropic, right? So that means that when you see clusters and galaxies, you kind of hope that if you go on larger and larger scales, the universe will start to look uniform. And there were redshift surveys of galaxies when this started being formed. The first redshift surveys, which were three-dimensional surveys of galaxies, they showed that the galaxies are distributed in some kind of a web form, filamentary form, and you saw these very large filaments. These are simulations. These are actual distributions of galaxies that slice through a redshift survey. And you can see these are very large filaments of galaxies. And then slowly we started figuring out, these come from theses of students that have worked with me in the past, um, uh, and discovered these very interesting structures in which you can see these are filaments that contain lots of clusters of galaxies. So these are clusters of galaxies, right? Shapley supercluster, for example, which was discovered towards the end of the 80s and beginning of 90s, has 40 clusters of galaxies in here. And Pisces Cetus is about 30 clusters. You can see each of these clusters. They are in these large shapes. So then you can ask the question, how large do you have to go in the universe before it starts looking homogeneous? And the interesting thing is we have not, uh, we don't have a measure of that yet. Because the larger we look, the bigger maps we make of the three-dimensional distribution of galaxies, the more of these structures come. And it's very interesting, even though we assume the universe to be homogeneous on very large scales, we have not reached that. Astronomy is a very young subject. We have not reached that kinds of surveys of volumes, making maps of the universe, such that we have come to a stage where we can look at a uniform distribution of galaxies, right? Here's an example of one of the largest such structures. This is called the Sloan Great Wall, which is about 200 megaparsecs long, right? I told you that the distance between galaxies is about a megaparsec. A cluster itself is a couple of megaparsecs across, but has it's a filament that's 200 megaparsecs long, and it has about 25 to 30 clusters embedded in it. So this is what I call a supercluster, and these are now becoming quite interesting to find out what the largest structures in the universe are, etc. We are actually, so you can see these are simulations, of course, and you can see this filamentary structure as you go. This whole thing is about 300, 400 megaparsecs on a side, and you can see all these little filaments in there. If you go to Wikipedia, the latest Wikipedia article on superclusters lists some of these superclusters around us. We are in the middle of this sphere, and you can see that there are all these superclusters that people have found, which are very filamentary, and each of these have many, many clusters in them. And so this is another very nice and emerging field in which it is very young, because the kind of work that I showed you that has been done with clusters, which means that you look at X-rays in them, and you look at the lensing reconstruction of dark matter in them, has not yet been done very well with superclusters. We can see them as connections of objects. You can see lots of clusters. You can detect individually through X-rays and in optical maps, and you can see the connections. But if somebody comes and asks you, have you done a lensing study of the amount of dark matter that's in the Hercules supercluster? This is a completely open question. It's only starting this subject. It's just a young subject, and I thought I'd represent this in this kind of summer school where there are young people and then there are their teachers who can all see that there's an emerging field which asks these questions: is dark matter more important in superclusters than in clusters? Are superclusters just an addition of clusters strung together like a necklace? But is there a overarching dark matter around a supercluster? We don't know. Just like when we looked at galaxies and then we went to clusters, and then clusters has much more dark matter than in the galaxies themselves. We don't know whether superclusters have more dark matter around them than the clusters themselves. Young subject, we don't know. Also, we don't know, but we know that these superclusters are parts of the cosmic web. And that is where there are lots and lots of galaxies and their groups and clusters. So they're all threaded together in these segments of the cosmic web. And the more we make maps, three-dimensional maps, it's a big, big thing now. Lots of surveys coming up, ground-based and space-based. We will slowly begin to see this actual structure of the galaxies around us. This is called the Laniakea Supercluster. This is our own supercluster. We are part of it. The Milky Way is part of this particular supercluster. It's a very interesting structure. It is a Hawaiian name because it was discovered by or characterized first by Brent Tully, who's at the University of Hawaii. And so this is home for us, right? So we live in the Milky Way, which is a galaxy, which is part of the local group, as you know, which is on the outskirts of the Virgo cluster. They're all in the middle somewhere there. And the Virgo cluster is part of the Laniakea Supercluster. And so here you are. And but then the fact that how many of the other clusters are there, and all this is now being discovered. We here at IUCAA were very fortunate to discover one of these superclusters. Joydeep Bakchi, who was a professor here, and some of us worked together for many years to find another of these systems, about 200 megaparsecs long, has about 40 massive clusters, and the mass, as you can see, of at least 10 to the power 16 times the mass of the sun. Remember, the Coma Cluster mass came to be 10 to the 15. This is many more clusters in them. So we don't really know how much dark matter there is, but we can measure this thing, and that whole chain that's in there. It's very far away, which is why it looks small, but it's 200 megaparsecs across, and it's much further away than all those superclusters that you saw. And this came out of a survey from the Sloan survey. When we discovered it, it became quite famous. It came out in newspapers. You can see tweets from ministers and chief ministers, etc., congratulated us. But the most important thing that I want to end with is that it became the final question in Kaun Banega Crorepati. And so if you had listened to these lectures, and this contestant who went, in those days, the prize was still 1 crore. This is 2017. And in the last question, Amitabh Bachchan asked what was the name of the supercluster of galaxies discovered by Indian astronomers. And this person could not answer. So there you are. That's one of the utilities of attending a summer school like this. Now you know the answer to this question. And so on that note, I wanted to end these lectures on the larger structures in the universe. This is a subject that is unfolding. It's becoming more and more interesting. And we first discover the different structures and then study them using X-rays, using lensing, using optical and other studies of using different telescopes, and then maybe answer the question of what happens on very large scales, what are the largest structures in the universe. So I'm going to stop sharing and see whether anybody has any questions in the last 5 minutes or so. You can put up your hand and ask questions. If you have written them in the Google form, then we will put answers in the Google form later on. But let's see if anybody else has any questions now. No? I was looking at the chat box to see whether there's anything there. Okay, then if there are no more questions, thank you very much for listening to me. You've been with me for 6 lectures.
Yes, sir.
And,
Excuse me, sir.
Yes,
sir, I am Devesh. Sir, I want to ask a question. Sir, sir, I want to know that, sir, why the universe is isotropic? Sir, that it looks same from every direction. Like, sir, if our Earth is in the Milky Way galaxy, if it would be in a far off distant cluster, then it would look the same. I think that means isotropic. If that is so, then why is it, sir?
No, if you assume, if you're doing cosmology, theoretical cosmology, if you assume the universe is homogeneous and isotropic, then it just means that the mathematics is simple. And that's what people do. Then you can be an observational cosmologist and ask the question, is there any evidence that the universe is homogeneous and isotropic? There's a lot of difference between those two terms. Homogeneous means that you take any volume in any chunk of the universe, a large enough volume, and it will have the same mean density, right? So that doesn't work if you have large filaments that span the whole universe. Then, of course, not all volumes that you can take at random will give you the same density. So that's homogeneity, and that's what I'm saying is we are trying to figure out what is the scale of homogeneity, what is the largest volume that you can fit in, such that you can say that it's the same everywhere. Isotropy is a different question altogether. Isotropic means that every direction, the distribution is more or less the same. And that is related to the question, is the universe rotating as a whole? If the universe rotates, then the universe won't be isotropic. Okay. And this, Hawking wrote some very interesting papers in the 1970s when the cosmic microwave background was found. And from the quadrupole anisotropies of the cosmic microwave background, he came to the conclusion that the universe, there is a very strong upper limit on the rotation of the whole universe. And if you are interested, go and find these papers. You will find a lot of papers have been written on it. So there is a limit on the net. And if the universe is not rotating, then the universe can be isotropic if it's homogeneous. Okay. Saurabh Upare.
Am I audible, sir?
Yes.
As I have read once, the Coma Cluster was used to study very earlier galaxy, by using the gravitational lensing. I have read one of the papers. So same applies for the superclusters as
Coma
they are
cluster has
huge.
not Coma cluster has not been used for gravitational lensing at all. In fact, Coma
Uh,
cluster is very nearby. The gravitational, it's very difficult because it's so large in the sky that it's difficult to measure gravitational lensing. Coma cluster
but
was
but
Coma
if
cluster was used for the dynamical measure of mass. Yes, I don't
uh,
think anybody's done gravitational lensing on Coma cluster.
but if we apply gravitational lensing for a galaxy like a cluster of galaxies for a huge mass, so the same applies for the supercluster. If we
Yes,
can,
but nobody's done it yet. The supercluster also, you can measure the amount of dark matter by gravitational lensing. It is harder to do because the superclusters that I talk about are very large, and so the density, actual projected density on the sky is much smaller, and so you will have to use weak lensing. And on supercluster scales, only a couple of papers have come out which have claimed to do something like that. It's not very established yet, but it's a new subject. I hope that Dr. Morey will talk about it when he talks about weak lensing and cosmic shear, when in the gravitational lensing lectures. But on supercluster scales, it has to be done and has not been done yet. On cluster scales, it has been done, and only since the 1990s, when the Hubble Space Telescope took such amazing pictures that lensing could be used on clusters. Okay. And I can see that you've got the bullet cluster as your
bullet cluster,
profile
yes.
picture, which is beautiful.
Yes, sir.
Akshat, your question.
Sir, my question is that by which of the methods that you mentioned today was the mass of Saraswati supercluster determined?
The mass of the Saraswati supercluster is entirely determined by uh, by uh, uh, dynamical methods, because we have not. There is another. For the Saraswati supercluster, there are 42 clusters in it, out of which about 15 or so we have measured the X-ray mass of the individual clusters because they are very bright in X-rays. A whole X-ray survey of the Saraswati supercluster has not been done yet. We are doing it. It's slowly being done. We are also doing a redshift survey. It will take a very long time. It's quite far away compared to the other superclusters, the ones I showed, the Shapley and the Hydrocentaurs, etc. They're nearby. They are within, say, 200-300 megaparsecs. Saraswati supercluster is 5 times further away. So it is a challenging thing, and we're trying to do. So we know the X-ray masses of some of the clusters, but not the whole supercluster. We have no lensing data yet on the Saraswati supercluster. It can be done, but nobody's done it yet. And so the way that mass estimate that we had in that paper came just from the dynamics of the galaxies in the clusters and applying the Weyl theorem, which is not a very good way of doing it, because clearly for a supercluster, it is a dodgy assumption to make that they are in equilibrium. But what we did was we added up the masses measured by dynamics and X-rays of the individual clusters, put them together, and that's why I say at least 2 times 10 to the 16, because actually it should be much, much bigger than that. I think it might be as big as 10 to the power 17 or more. And then comes the question of, is there extra dark matter along a supercluster that is not the dark matter around the clusters themselves, but the dark matter of the supercluster? This answer is not there yet. We don't know. Anybody else? Okay, then I'll sign off. Thank you very much again for listening to me, and I hope you enjoy the rest of um, the lectures in this summer school refresher course. Thank you very much. If you have any other questions, please put it in the Google form, and we'll try to answer.